All right, so we are continuing with 8.1 today, which is structures of the circulatory system. So we're going to talk about the beating heart. So the stimulus that triggers a heartbeat is an electrical signal, and it originates from within the heart itself. So the rate and strength of a heartbeat is under the control of the nervous system, but the stimulus that triggers a heartbeat is actually an electrical signal that comes from within the heart itself. So there's a bundle of specialized muscle tissue and called the sinoatrial node, or the SA node, and it stimulates the muscle cells to contract and relax rhythmically. It's also called the pacemaker. So this SA node may also be called the pacemaker. Reason being, it sets the pace for cardiac activity. So this SA node is located in the wall of the right atrium, and it generates an electrical signal that spreads over the two atria and makes them contract simultaneously. And then there's another node called the atrioventricular or AV node. So as the atria contract, the signal reaches this node, the AV node. And the AV node transmits the electrical signal through a bundle of specialized fibers called the bundle of His. And these fibers relay the signal through two bundle branches that divide into fast conducting Purkinje fibers, which initiate the almost simultaneous contraction of all cells of the right and left ventricles. All right, so here we see the SA node right here in the right atrium. Here is the AV node, and then the bundle branches are here, the bundle of His. This is the left ventricle, here's the right ventricle, and these here is showing the Purkinje fibers. All right, so the SA node sends out an electrical stimulus, which causes the atria to contract. That stimulus will reach the AV node here and then get passed through the bundle of His and the Purkinje fibers. That stimulus causes the ventricles to contract, starting from the apex, right here is the apex of the heart, and then upward. All right, and that forces the blood towards the pulmonary artery here, or to the aorta here. The chordae tendineae and the septum there, the chordae tendineae here, which are shown like right here, are strong fibrous strings, and they prevent the valves in the heart from inverting when the heart contracts. All right, so the beating heart, the change in voltage produced by the electrical signal can be measured using an electrocardiogram, an ECG. And it records the electrical activity of the heart as it contracts and relaxes. All right, so here we have the SA node. There's that's when the atria contract, and we can see what's happening here in this electrocardiogram. All right, the impulse gets delayed at the AV node, the ventricles start to fill, and here's what we're seeing in our electrocardiogram. Then we have the ventricular excitation in the heart apex. The bicuspid and tricuspid valves close, so we can see it shown right here on our graph. The ventricular excitation is complete, and we can see the blood flowing now into the pulmonary artery and towards the aorta. And then there's ventricular relaxation, the semilunar valves close. Okay, so here we would hear that lub sound, and here is the dub sound. So the lub-dub sound. So blood pressure. As blood passes through the vessels in the body, it exerts pressure against the vessel walls. And when the ventricles contract, and force blood into the pulmonary arteries and the aorta, the pressure increases in those vessels. The maximum pressure during the ventricular contraction, that's called systolic pressure. And the ventricles will then relax, and the pressure in the pulmonary arteries and the aorta will drop. And then that lowest pressure before the ventricles contract again, that's called the diastolic pressure. And it's recorded in millimeters of mercury, or mmHg, that represents millimeters of mercury. And it's done using a device called a sphygmomanometer. All right, and here just a conversion, 1 millimeter of mercury is equal to 0.133 kilopascals. The systolic pressure is presented over the diastolic pressure in the form of a fraction. And what you normally see in an average healthy person is below 120 millimeters of mercury over 80 millimeters of mercury. So as a fraction, it would be 120 over 80 for an average healthy young person. All right, cardiac output and stroke volume. So the amount of blood pumped by the heart is called the cardiac output, and it's measured in milliliters per minute. So the cardiac output, it's an indicator of the level of oxygen that's delivered to the body and the amount of work the body's muscles can perform. So there's two factors that affect cardiac output. First one is heart rate, and the second is stroke volume. So the heart rate is the number of heartbeats per minute, and the stroke volume is the amount of blood forced out of the heart with each heartbeat. So your cardiac output then is your heartbeat times your stroke volume. All right, shown right here. So the average person has a stroke volume of about 70 milliliters and a resting heart rate of about 70 beats per minute. So their cardiac output would be about 4,900 milliliters per minute. The average person has about 5 liters of blood in their body. So therefore, the total volume of blood in the body circulates through the heart about once every minute. All right, here we're just looking at the relationship between stroke volume, heart rate, and cardiac output. So we have 3 individuals. We're looking at individual A, B, and C. We can see their resting heart rate. So 70 beats per minute, 98 beats per minute, and 35 beats per minute. Here is their stroke volume in milliliters per beat. So 70 milliliters per beat, 50 milliliters per beat, and 140 milliliters per beat. And then their cardiac output is 4,900 for all 3 individuals, 4,900 milliliters per minute. So if we look at individual C, resting heart rate of about 35 beats per minute, but their stroke volume is 140 milliliters per beat. So individual C's heart is exceptionally fit, having a very high stroke volume. Individual C can basically maintain the same level of cardiac output, which is their oxygen delivery, at a much lower heart rate than the less fit heart of B or the average heart of A. So basically, this person, individual C, their heart is working more efficiently than person A or person B. A low resting heart rate is considered an indicator of cardiovascular fitness because it means that their stroke volume is high. So strong hearts, they can pump greater volumes of blood with each beat, and that's why athletes often have low heart rates. And hearts that are less strong are unable to pump as much blood per beat, but they compensate by increasing the heart rate to meet the body's energy demands. All right, next is heart rate recovery. So how long does it take your heart to return to its resting rate? All right, so that you can do this. You can find your pulse at your wrist, or under your jawbone, and you can record your pulse for 15 seconds and then multiply by 4. That's your resting heart rate. Next, what you would do is some sort of exercise like jumping jacks for like a minute. Immediately then, you would take your heart rate at the end of that exercise. So you would continue taking measurements every minute until your heart rate has returned to your resting rate. Then you can plot these results on a graph, heart rate versus time. And if you have a short recovery time, it's associated with an efficient cardiovascular system. All right, if you have a physical condition or you're not, it's not advised for you to exercise vigorously, you can do this alternative. You can record your resting heart rate, then sit quietly, breathe deeply, relax your body, and then after 4 minutes, check your heart rate to see how much you've lowered it. And then you can take those readings for every minute until your heart rate returns to its resting rate. And then again, you can plot your results on a graph of heart rate versus time. All right, so next we're just going to review the pathways of the circulatory system. So this will be a little bit of a review. So the 3 pathways of the circulatory system. The first is the pulmonary pathway. Every time you see this word here, pulmonary, it means lungs. It's pertaining to lungs. So the pulmonary pathway. This is the transport of oxygen-poor blood to the lungs. So when the blood then reaches the lungs, oxygen and carbon dioxide are exchanged by diffusion between the blood in the capillaries and the air in the lungs. And then oxygen-rich blood will return to the left side of the heart by way of pulmonary veins. The other pathway is called the systemic pathway. This is the movement of that oxygen-rich blood from the left ventricle of the heart to all of the body tissues. All right, so oxygen and the nutrients will move into the tissue cells. The waste products will move out of the tissue cells and go into the blood. All right, and that includes the carbon dioxide, which is a waste. And the last system is the coronary pathway, which is providing blood to the muscle tissue of the heart itself. So coronary pertaining to the heart. All right, so this diagram is showing the pulmonary and systemic pathways. All right, so this is in the middle is the heart. And reminder that the blue always represents the deoxygenated blood or blood that's low in oxygen. And then the red shows blood that is high in oxygen or oxygenated blood. All right, so tracing the flow of blood through the pulmonary and systemic pathways. So arteries, they carry blood away from the heart. Veins carry blood towards the heart. All right, in the systemic pathway, arteries carry oxygen-rich blood, shown in red, and veins carry the oxygen-poor blood, shown in blue. The reverse is true in the pulmonary pathway. Arteries are carrying the oxygen-poor blood, and veins are carrying the oxygen-rich blood. All right, that's the exception, is here in the pulmonary arteries and veins. All right, so here what we can see is, if you remember from last class, we have the superior and the inferior vena cava enters the atrium here. The right atrium gets pumped to the right ventricle. From that ventricle, the blood gets pumped to the lungs. All right, so your right and left lung. Here in the lungs, the carbon dioxide gets dropped off and the oxygen gets picked up. All right, so now we can see our blood is now red, and now the blood is going to return to the heart. It will enter the left atrium. From the left atrium, it will go to the left ventricle. Then that left ventricle is now going to push the blood to the aorta. The aorta will then take all of that oxygenated blood to the rest of the body. All right, so here to the head and neck, as well as to the rest of the body, all the liver, the intestines, the kidneys, and so on. All right, so here it's just a summary of what I just talked about using that diagram. So tracing the blood flow through the pulmonary and systemic pathways. So oxygen poor blood enters the pulmonary pathway, first flowing through the vena cava into the right atrium. The atria contract, the blood gets pumped to the right ventricle. The ventricle will contract and the blood will get pumped to the pulmonary trunk, which will then divide into the left and right pulmonary arteries. The pulmonary arteries will then go to the left and right lungs. That's where gas exchange occurs. Okay, the blood will pick up oxygen from the lungs and drop off the carbon dioxide. That freshly oxygen-rich blood will now go from the lungs and go to the left and right pulmonary veins and enter the left atrium of the heart. Okay, now the blood is entering the systemic pathway. The atria will contract and pump the blood to the left ventricle. From the left ventricle, the blood will go to the aorta. The aorta will then divide into large arteries and supply the blood to the body tissues. Okay, the coronary pathway, this is when the heart itself is supplied with blood. The heart doesn't use the blood inside its chambers to get the nutrients and remove waste. That's what the coronary pathway is for. The coronary pathway provides matter and energy to the cardiac muscle cells by way of capillaries that are embedded directly in the heart wall. The entire surface of the heart is covered in a network of tiny blood vessels that encircle the heart. So the oxygen-rich blood moves through these vessels into the capillary bed. Gas exchange will occur between the capillaries and the cells of the cardiac tissue. The oxygen-poor blood will then flow out into the vessels that will get progressively larger and then into the coronary veins. The coronary veins join together and the oxygen-poor blood will enter the right ventricle and go back to the lungs to pick up more oxygen. All right, so this is just showing the coronary pathway here. We can see that network of vessels shown around the heart here. All right, and lastly, we're going to talk about cardiovascular disorders and treatments. So cardiovascular disease is the leading cause for death for Canadians. Arteriosclerosis, that's the general term used to describe several conditions in which the walls of arteries thicken and they lose their elastic properties and become harder. Atherosclerosis is the most common type of arteriosclerosis. So basically what happens is there's a buildup of plaque, which includes fatty deposits, calcium, and fibrous tissues. And this buildup of plaque is on the inside of the artery walls. So the artery narrows because of this buildup, and therefore blood flow is decreased and blood pressure is increased. And this can lead to angina. Angina is chest pain. It can lead to blood clots, shortness of breath, heart attack, or even heart failure. So here in figure A, this is a normal artery. All right, nice and open space for blood flow. Here is a cross-section of artery. This is a person that has atherosclerosis. All right, so a lot of buildup of plaque and a very narrow passageway for blood flow. All right, very narrow passageway. This will also increase blood pressure. Treatment for atherosclerosis, things like exercising, not smoking, eating a diet low in saturated fats and high in fruits and vegetables contribute to reducing the risk of developing this condition. Aspirin is taken. It prevents platelets from sticking together, so it reduces the formation of blood clots. Angioplasty, it's a procedure where a surgeon inserts a tube into the clogged artery, shown here. And then when the tube reaches the site where the artery is clogged, a tiny balloon is inflated to force the artery open. And then sometimes a small permanent metal tube, it's called a stent, is inserted into the blockage during the procedure. And that stent will just hold, it'll hold the vessel open, and it reduces the chance of the blockage redeveloping. All right, so here we can see this is a closed artery, inserted a balloon here, and then inflate the balloon to keep it open. And then a metal stent is inserted to keep it open. A coronary bypass operation, this is when a segment of healthy artery or vein is taken from elsewhere in the body and used to create a new pathway around a blocked vessel near the heart. All right, so shown here, these are 3 blocked vessels here, and then these are the new ones, 1, 2, 3. They're grafted veins, they will carry arterial blood. So because there's 3 done here, this is called a triple bypass. So meaning 3 new pathways were constructed to avoid blockages in these 3 blood vessels. All right, one end of the new segment is attached to the aorta right here, and the other end is attached to a point in the blood vessel beyond the blockage to bypass it. And then the words double, triple, they refer to the number of vessels with blockages that had to be bypassed. Congenital cardiovascular problems, these are defects in the heart that have been present since birth. They include problems in the walls dividing the chambers of the heart, in the valves, or in the structure of the blood vessels near the heart. So there may be a heart murmur, which means there's a misflow of blood through the heart, such as one or more of the valves are not opening or closing properly. And then these valve defects can be heard with a stethoscope. It'll be heard as like a whooshing or rasping sound, which is caused when blood is leaking through the valve. And this is a magnetic resonance imaging scan. All right, an aneurysm. This is a bulge that forms in the wall of a weakened blood vessel, usually an artery. All right, so this is an artery here. We can see this bulge. So that's the weakened area of that blood vessel. So the most common sites are the aorta of the heart, the abdominal aorta, and arteries in the brain. And these aneurysms are often due to atherosclerosis. So in much the same way as the weakened wall of an inner tube begins to bulge, the weakened segment of the artery protrudes as blood pulses through. The inner wall offers less support and will eventually rupture, so shown here. Because it's ruptured, less oxygen and nutrients are delivered to the tissues, which will result in cell death. And if it happens in the brain, it's one of the conditions that causes stroke. All right, so quick summary here for the beating heart. The right side of the heart contains deoxygenated blood received from the body. It gets pumped from the heart to the lungs. The left side of the heart will now contain oxygenated blood from the lungs, and it will get pumped out to supply the body's tissues. All right, blood flows simultaneously into the top 2 chambers of the heart, which are the atria. The atria contract together to pass blood through the atrioventricular valves and then passes into the ventricles. The ventricles will also contract synchronously to push blood from the heart. The signal that triggers a heartbeat begins in the SA node, which will stimulate the cardiac muscle cells to contract and relax rhythmically. Message from the SA node goes to the AV node, which will signal the Purkinje fibers. The pumping action, the muscle contraction and relaxation, is coordinated by these Purkinje fibers located in the inner ventricular walls of the heart. All right, these fibers are specialized myocardial fibers that conduct an electrical stimulus or impulse, which enables the heart to contract in a coordinated fashion. All right, and then we talked about the pulmonary circulation versus systemic circulation. So pulmonary circulation occurs when the right side of the heart pumps the deoxygenated blood to the lungs by the pulmonary arteries. The pulmonary veins will bring the oxygenated blood back to the left side of the heart, and then it will be distributed to the rest of the body. All right, so in the pulmonary system, arteries carry deoxygenated blood and the veins are carrying oxygenated blood. Okay, that's different from the systemic circulation. In systemic circulation, blood is being carried to all parts of the body, but not to the lungs. All right, this is the portion of the cardiovascular system in which arteries are carrying oxygenated blood away from the heart to the body and all the body's tissues and cells, and then the veins will return deoxygenated blood back to the heart. All right, and then we had talked about heart rate, cardiac output, which is the amount of blood pumped by the heart each minute, measured in liters per minute. It's an indicator of the level of oxygen delivered to the body. The amount of work that a body's muscles can perform depends on the oxygen available to them. So cardiac output is a product, or when you multiply heart rate and stroke volume. All right, heart rate is the number of times your heart beats in a minute. Average resting heart rate is about 70 beats per minute. So on average, your heart will beat close to 3 billion times over a lifetime. And more than 200 million liters of blood will pass through its chambers. Stroke volume is the amount of blood that's pumped from the heart with each beat. A strong heart has the ability to pump a large volume of blood with each beat. So it doesn't have to contract as much in order to circulate blood. All right, so that results in a lower heart rate and greater work capacity. All right, so athletes that do intense cardiovascular training, they have the most efficient work output with the least amount of energy. So they achieve low resting heart rates due to the strength of their heart muscles developed as a result of rigorous cardiovascular activities. All right, here we're just looking at blood pressure, which is the force exerted by circulating blood on the walls of blood vessels. So blood pressure as well as pulse makes up the vital signs. The pressure of the circulating blood decreases as blood moves through arteries, veins, and then to the capillaries. So the term blood pressure generally refers to arterial pressure, and it's measured using a sphygmomanometer, and the pressure is usually in an artery of your arm that's measured. Okay, the two measurements were diastole and systole. Systolic pressure is the peak pressure in an artery at the beginning of the cardiac cycle or during ventricular contraction, and then diastolic pressure was the lowest pressure during the resting phase of the cardiac cycle or when the ventricles are relaxed. And then it's always the ratio of systole over diastole. All right, just a few questions here. What blood vessels carry blood away from the heart? Those are arteries. One way to remember that was A for arteries and A for away. Question 2, what blood vessels carry blood to the heart? Those are veins. Compare the structure of the three types of blood vessels. So veins, they are not elastic. They have valves to move blood back to the heart. Otherwise, blood would pool in the extremities like your legs. Arteries are elastic, so they can expand with the force of blood as it pumps from the heart. Arteries expand as ventricles relax and keep the blood flowing. And then capillaries are the very small blood vessels, and they spread out in a network that allows single blood cells to be exposed to individual cells. What is the relationship between heart rate and blood pressure? So high blood pressure is linked to people with elevated resting heart rates. The heart is not pumping efficiently while the pressure is increased in the blood. Blood pressure will increase slightly during exercise to accommodate the need for a faster rate of blood flow. All right, there are a couple videos here for you to watch. We won't have time today, but the links are provided here.